Properties is there in some way the kind of minimal set of conditions, the minimal set of properties that you want the setup to have to be mathematically interesting. And this is a very common set of features to have when you've got a certain set and a certain meaningful binary operation. So we've discussed a number of examples, and last time we introduced the notion of permutations. Permutations, when you first see them, they seem like quite specialized, quite a kind of narrow type of thing. But it turns out that they are quite general in group theory. And I might explain that to you, explain that point in a moment. So what a permutation was, so we saw this last time, a permutation on n objects is a bijective function from that set of n objects to itself. Now, these objects that we're referring to don't have any kind of structure for us. We never inquire into the nature of these objects. What we're studying here is just functions, bijections, on a set of n different objects, and studying that system, the set of all bijective functions of the set. So it's traditional or convenient or conventional to just label these n objects using the integers 1 through n. Or you could label them with the first n letters of the alphabet. And when you gather all these bijections together, so remember a bijection is a one-to-one and onto function, an injective and a surjective function. When you gather these all together in a set, we call the set Sn, and it is going to be a group under the operation of composition. And it gives a very good model of a group that is a set of functions under the operation of composition. And it turns out to be quite universal for a reason that I might mention shortly. Now, in order to investigate these permutations and do calculations with them, we need a good notation for them. So the first notation that we introduced, this is all recapping last time, is the so-called two-line notation. So this matrix of two rows here, this completely defines a bijection sigma from the set of 4 objects to itself. Right? The convention is that the arguments 1 through 4 are put in the top row, and the corresponding values under sigma are put on the second row. So this particular sigma here represents the function that sends 1 to 2. Sigma 1 is 2, sigma 2 is 4, sigma 3 is 1, and sigma 4 is 3. Okay? Underneath each argument is the value of sigma on that argument. That's a pretty good way of denoting a permutation. In essence, it gives the essential information that's contained in an arrow mapping diagram. Diagrams like this, which we drew, first of all, to visualize the permutation, going from the domain, say, 1 through 5 here, to the codomain, 1 through 5. And you draw arrows to indicate the action of the function. Well, really, the two-line notation just gets down all the essential information from such arrow diagrams. Okay? The fact that this element gets mapped to that element, this element gets mapped to that element. So you don't actually need the arrows there, you just need the arguments of the corresponding values. We did a few examples. We saw how to compose these. So remember, the operation here is composition of functions. So from when you see a product like this, so this is 2 permutations from S8. This is what's being signified here is the composition of the one on the left after the one on the right. And by applying the rule of function composition there, you could construct a two-line notation for the result of that one. We then went on to describe how there's a different type of notation for these. And this is the so-called cycle notation. Very quick review. We looked at an example, not sure if we chose exactly this example, but we looked at an example like this. So this mu here, which we're showing, this is a two-line notation symbol for a permutation on 8 objects. Okay. Now, it's not so apparent from the two-line symbol, but if you actually draw if you put the 8 objects down on the page and draw arrows between them to signify the action of mu, you actually start to see some of the inherent structure of the permutation, which isn't readily apparent in the two-line notation. So we're just using one set of labels, 1 through 8 here, not a separate set for the domain and a separate set for the coding. Just one set. And we're drawing arrows to show the action of mu. So mu sends 1 to 7, for instance. It sends 7 to 2, and so on. But when you draw all these arrows, you see that the permutation mu naturally breaks down into a set of disjoint cycles. Okay. So there's a cycle of 3 elements here. 1 goes to 7, goes to 2, goes back to 1. 8 goes to 4, goes to 3, goes back to 8. 6 goes to 6, 5 goes to 5. So you can see here how mu has this inherent structure of 4 different disjoint cycles in it. So that leads us to having a special notation to denote one of these cycles. And what's what's all the essential information you need to know about, say, this cycle here? 1 goes to 7, goes to 2. The essential information about that cycle is just what the cyclic order of the elements is as you go around the cycle. 7, 2, and then 1. So you just need to record 7, 2, 1 in that order, and that uniquely defines that cycle. Of course, you could also denote it as 2, 1, 7. It's still talking about the same cycle. It's a cycle, it's a closed loop. It doesn't have a beginning and an end. It's a closed loop, so you can choose to start anywhere. So equally well, you could denote it by 1, 7, 2. Of course, you wouldn't describe it as 1, 2, 7. That's going through the elements in the wrong order. 1, 2, 7 would be a different cycle. This is the cycle 1, 7, 2. 1, 7, 2. And the compact notation we have for cycles is this kind of notation here. So that one line of labels there, 1, 3, 5, 2, 4, that denotes this permutation. It sends 1 to 3, sigma sends 3 to 5, 5 to 2, 2 to 4, and the one at the end, it sends back to the first line. So this sigma here, 1 goes to 3, 3 goes to 5, 5 goes to 2, 2 goes to 4, and 4 goes to 2. That sigma there is denoting that cycle. Of course, equally well, you could also denote it as 5, 2, 4, 3, 1. There is no preferred starting. And using this idea, so this is where we ended last time, we have this idea that permutations always have a nice expression as a product of disjoint cycles. So this one we could denote, if I've seen the cycles down here, this is the cycle 1, 7, 2, after the cycle 4, 3, 8, and the cycle 5, and the cycle 6. Those last two ones we put down there are so-called trivial cycles, cycles of length 1. And we have this convention, it was mentioned in the definition here. By convention, any label that's not mentioned in the cycle, the permutation, you can consider it to be still acting on that label, even if the label isn't mentioned here. But the convention is that this sigma will leave that label unchanged. So if we declared up here that this sigma I'm talking about here was in fact an element of S8, well, there are some labels from the set 1 to 8 not mentioned at all here, namely 6, 7, and 8. But the conventional understanding is that sigma still applies to those, but they leave each of them fixed, because they're not mentioned in the cycle. They're not part of the cycle. So sigma of 6 would equal to 6, sigma of 7 would be 7, sigma of 8 would be 8. If it was declared or understood that this sigma was an element of S8, the symmetric group of all permutations on 8 objects. With that understanding then, we can then denote any permutation as the product of its disjoint cycles. And this kind of notation is essentially unique. But there are a number of different strings of symbols that will still denote the same permutation. Because these cycles are disjoint, I can actually fool around with the order in which they're multiplied or composed. Because they're all operating on different elements, they do all commute with each other. Because one of the cycles is an action over here that does something to elements over here. Another one is an action that does something to a different set of elements over here. So it doesn't matter if you do this one first and then that one, or that one first and then this one. The overall effect is the same, is to have moved each of the elements on in their own cyclic order within their cycle. So while in general permutations do not commute because they're functions under the operation compositions, in general it makes a difference in the order in which you do things. But if the functions are acting on completely separate, disjoint sets of objects, then it doesn't matter in what order you do. Then there's also by this convention that if a label isn't mentioned, the permutation leaves that label unchanged. You don't actually have to include the trivial cycles in the notation. So those can be dropped as well to give a slightly more compact form of notation. Okay. So this mu, we can view it kind of much more meaningfully as the product of these two disjoint cycles. So that's, in some sense, that's the preferred type of notation for a permutation. It records all the essential information about the permutation with the addition of knowing which group the permutation is in. So that would be by some kind of declaration, for instance, here that it's in S8. Because you need to know about the labels that aren't mentioned explicitly here. But this kind of notation contains all the essential information about this permutation. And it's very efficient. It doesn't require that many characters to write it down. And it's preferred over the two-line notation because, well, the two-line notation is slightly wasteful because you're always, the top row is always going to be the same. And the fact that there are these cycles here doesn't leap out at you from the two-line notation. You have to kind of investigate it to discover the cycles. Whereas the cycles are very apparent and explicitly presented there in this disjoint cycle notation. Now, the only bit we didn't get to, which was just at the bottom of this page 69 here, was to talk about just yet another type of notational form, although it still goes under the heading of cycle notation, products of cycles. And this is, well, there's a special terminology given to cycles of length 2. So transposition is a cycle of length 2. So any sigma which looks like this, AB, which is a cycle of length 2. So we have two elements here, A goes to B, and B goes to A. It's kind of special kind of cycle. It's a cycle of minimal length. It's the shortest non-trivial cycle that you can have. And it's this basic operation of just swapping the positions or interchanging two elements. And there's a little, I mean, it's hardly a theorem really, it's just an aspect of the notation, is that any cycle, so this symbol here on the left, A1 up to AN, this is a generic cycle. It's a cycle of length M. A cycle of length M can always be written as a product of the transpositions. There's a few different ways to do it, but this is one way. And so we've got the transposition A minus 1 AN at the right, and to the left of it, the transposition AM minus 2, AM minus 1, and so on. You keep working backwards, you'll have A3, A4, A2, A3, and finally A1, A2. Now the reasoning behind this can be quite easily visualized. You just imagine these objects A1 through AN as, so I'm setting down 5 pens there. So the instruction on the left is to cyclically permute those M objects, okay, we're taking M equals 5 here, to send them around in a cycle. So each one goes to the position of the next one, so this pen goes to here, 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 and the one that was at the end is sent back to the start. Okay? So that's us applying the cyclic permutation to the 5 pens. I'll apply it again. You just move every pen on one position, and the one that was at the end you send back to the start. That's the whole 5 cycle kind of applied in one go. What's on the right-hand side is applying these, applying that action of applying the whole cyclic permutation, but just by applying a sequence of transpositions. Okay. So if you take these pens as being labeled A1 here on your right, then A2, A3, A4, A5. The instruction on the right, okay, this is a composition of transpositions. So it's a composition, so the first function applied is this one on the right. And this says to, I'm going to put the red one at the end so you can easily track its position, one with the red cap. The product on the right says, first of all, swap the elements in position AM and AM minus 1. Okay? So that is swapping those two. Then the next permutation to apply says swap the things in position AM minus 2 with AM minus 1. So that says transpose these two. We keep going down. So now we'd be at this second last one, A2, A3. Transpose the objects in positions 2 and 3. And then finally, do A1, A2, transpose the objects in positions 1 and 2, and do that. Okay. Now, what has happened to my starting configuration of pens is at the beginning, they were all like this. And then I swap those, swap those, swap those, swap those. In effect, we've just applied exactly the cyclic permutation from the left-hand side. Each pen has moved on one position to your left, it's moved on one click to your left, and the one that was at the end has gone back to the start. Okay? So we've exactly applied that cyclic permutation, but viewed it as a product of these transpositions. So that's an important type of notational form to know about for permutations, because it shows how any cycle can be realized as a product of these minimal, non-trivial cycles. Now you do notice as well that, of course, the expression on the right, it's a product of cycles, but they're not disjoint. Okay? Each two cycles that are next door to one another, share a label. So they're certainly not disjoint cycles. Remember, disjoint cycles are cycles which don't feature any label in common, like these ones here, 438 and 172. Those are disjoint. They don't share any labels. So we could look at an example here now. So it's example 5.10. And the instruction here is this is just working with this new type of notation. The instruction here is to express the following permutations from S5 as products of transpositions. So we're starting off with the 2-line notation here. So let's look at question 1. So it's 1, 2, 3, 4, 5. So these are permutations from S5. 2, 4, 5, 2, 1. Well, first of all, we want to, in order to get to the transpositions, first of all, we want to discover the disjoint cycles that there are. So I won't choose 1 as a starting point, just to emphasize that nothing special about 1 in this picture. So one of the disjoint cycles is going to have a 3 in it. Okay? So we're going to start to discover what it is. So I put down my 3. So in the cycle that has 3 in it, something's going to come after it. So what comes after it? Well, you see, sigma sends 3 to 5. So the object that comes after 3 in its cycle is 5. So we've discovered the start of this cycle. Then you look and see what sigma does to 5. Sigma sends 5 to 1. So 1 is the next element of the cycle. So we're just step by step discovering one of the cycles. Then we ask what comes after 1. You look at what sigma does to 1. Sigma sends 1 to 3. So maybe I'm tempted to put a 3 down there, but no, I notice that 3 is the same element I started off with. So that's the closure of that cycle. We've just discovered that these three elements are in a cycle of length 3 within the permutation sigma. Okay, so we discovered one of the cycles. Then you just start with one of the other elements that hasn't been mentioned yet. So the label 2. 2 is going to belong to some cycles. You see what sigma does to 2? Sigma sends 2 to 4. 4 comes after 2 in this cycle. Then what does sigma do to 4? Sigma sends 4 to 2. So that's back to the beginning of that cycle. So that's actually already a transposition cycle of length 2 within sigma. Okay, we discovered 2 cycles featuring the labels 3, 5, 1, 2, and 4, which is all the labels. Okay, this is something from S5. Sigma, because sigma is an element of S5. Okay, so there's nothing more of the structure of sigma to discover. So it's like a full stop there. And then to obtain that as a product of transpositions, well, 2, 4 is already a transposition. So we just need to decompose this 3 cycle into a product of transpositions, which we can do using that rule presented in theorem 5.7. So we start off by the transposition 5.1 and then follow that with the transposition 3.5. So now we have sigma expressed as a product of the transpositions. And we'll always be able to get to a representation like this because every permutation can be represented as a product of disjoint cycles, and each cycle can be decomposed using that rule into a product of transpositions. This also reveals something else about sigma. Sigma is said to be an odd permutation. And it's called an odd permutation because it has a representation as a product of an odd number of transpositions. Represented by an odd number of transpositions. And, okay, it's not something that we're going to prove, but it can be shown that there are, well, for a certain permutation, there might be many different ways of representing it as products of transpositions. We could discover even longer products of transpositions, which still give you the permutation sigma. But they will always feature an odd number of transpositions. Okay? The parity, the oddness or evenness of the number of transpositions required to represent a permutation is always a property of the permutation. It's always going to be odd, or it's always going to be even. Let's look at the second one then, question 2. So we're doing the same operation here. So here we have, say, a tau. 1, 2, 3, 4, 5. And we go 1, 3, 2, 5, 4. This is question 2. So again, okay, let's start at 1 this time. There's going to be a cycle featuring 1. Well, 1 gets sent to 1. So actually, 1 is just in a trivial cycle of like 1. So immediately we close the cycle notation. Then we start a new cycle, say 3, 2 gets sent to 3, but then 3 gets sent to 2. That closes off here. So actually this one is kind of rewriting itself, so to speak. 4 gets sent to 5, and 5 gets sent to 4. And by convention, we can drop the trivial cycle because it's understood that both of these permutations, when applied to 1, they leave 1 unchanged. They send 1 to 1. That's part of the convention about the cycle notation. So this is the expression of tau as a product of disjoint cycles, and it is also the expression for tau as a product of transpositions. Okay, because each of these cycles have length 2. And this shows tau to be even. Because it has an expression, it's a product of transpositions with an even number of transpositions. 2 here. And any other expression for tau as a product of an even number of transpositions, it will always have an even number. So, kind of the last fact that's said there is that the reason we might mention this oddness or evenness is that there's always, for any group, in any permutation group, in any of these symmetric groups, Sn, there's always an important subgroup, which is called the alternating group. The alternating group consists of all the even permutations. Okay? All those permutations which can be expressed as a product of an even number of transpositions. Okay? When you bring these all together, they form an important subgroup, and it's exactly half of all the permutations from the symmetric group Sn. So it has size n factorial over 2 because n factorial, remember, was the size of the group Sn. So that's kind of all we do with groups and permutations in this chapter. It's really just a first look at some of these things. There is a final year course on group theory, which delves into all of this in great detail. And you can kind of get something of a clue to the importance of permutation groups in general. See, when you first see them, permutations, as I said, they seem quite a specialized thing, quite a bijections on a set of n objects. Okay, what use are they to life in general? But they're actually quite universal in group theory, in the sense that any finite group at all is always going to be, it's possible to represent any finite group as a group, a certain group of permutations. And the reason for that can be appreciated quite nicely by considering the Cayley table. Now this is just from my own notes here, but remember a few lectures back we were looking at the dihedral group D3, the set of all symmetries of a regular triangle. We had rotations, E, the identity, rotating by 0 radians, R, rotating by 1/3 of a turn, R squared, rotating by 2/3 of a turn. And then we had 3 reflections, S1, S2, and S3. These were all reflections in one of these reflectional axes of symmetry of the triangle, which is an axis going through one of the vertices in the midpoint of the opposite side. Okay? The regular triangle, the isosceles triangle, has each of these 3 lines as axes of symmetry. Under reflection, the triangle as a whole is left unchanged. And we drew what's called the Cayley table, which was the multiplication table for this group. So you've got this in your notes from a few lectures ago. This is simply the multiplication table from the group. So the elements of the group are the symmetries. The operation is composition. And we have this convention here about what exactly we're composing. So an entry in the body of the table in row corresponding to the element Gi and the column corresponding to the element Gj. The element you're looking at is Gi after Gj. Gi composed with Gj. The Gi on the left and Gj on the right. We need that convention about which exact product we're looking at because composition is not commutative. So it does make a difference whether you've got Gi after Gj or Gj after Gi. Now, okay, what has all this got to do with permutations? And that's the question. But really, what we're looking at, although it might not be apparent until I copy down the table in a certain way, but what we're really looking at there is just a collection of permutations. Because if I simply choose to number the elements, so here we're forgetting about the kind of mathematical meaning of these elements. Some of these are rotations, some of these are reflections. If I'm just looking at the elements of the group just as distinct elements, I'm just going to label them with 1, 2, 3, 4, 5, 6. You see the first row, and then if I start to write down the first row of the table, well, because that's multiplication by the identity, that's simply the same elements written out again. If I write down the next row, so the action of R means this is 2, 3, 1, and 6, 4. So you just have to check the label each time. And if you look at the action of R squared, this is going to be 3, 1, 2, and 5, 6, 4, and so on. Because the elements in the table, the elements in the body of the table are all the elements from the group. So I'll be able to produce a kind of relabeling of that Cayley table just using the numbers 1 to 6. And then it's clear that what we're seeing here, associated to each element from the group, is very naturally associated to permutation of the elements 1 through 6. The identity is associated to the identity permutation. Sends 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, and 6 to 6. So here we're like looking at a bunch of 2-line symbols. This is the top line in each one, and these as the second lines in each one. So here we've naturally associated to the rotation R the permutation that sends 1 to 2, 2 to 3, 3 to 1, 4 to 6, 5 to 4, and 6 to 5. And that holds for each of the elements. Each element from the group is, when you look at the Cayley table, is naturally associated to a certain permutation of the labels 1 through 6. Okay. So this shows, so by relabeling Cayley table of a group G of order n. So the order of a group is just the number of elements that the group has in it. So by relabeling the Cayley table of a group of order n with the labels 1 through n, each element is naturally associated with a permutation from Sn. Sn, the symmetric group, is a group of all permutations of 6 objects. Now, the group S6 has size 6 factorial, so 6 by 5 by 4 by 3 by 2, and just somewhat big number, certainly bigger than the 6 elements that there are in the dihedral group D3. So by no means do you get all possible permutations of the 6 objects. You just get a subset of them. So in technical terms, this is the way we would describe it from a study of group theory in detail, that this group G, this finite group of order n, is the technical term used is that it's isomorphic to a subgroup of Sn. In group theory, isomorphic is this relation which essentially means the same group, or similar as groups, equivalent as groups. Equivalence of groups. So although 2 groups might consist of quite different objects, one might have some kind of number type objects, the other one might be some kind of matrices or something. But if the operation, if their 2 Cayley tables are displaying exactly the same structure, we regard the 2 groups as being equivalent as groups because they consist of the same number of elements and they combine together in the same way. So suddenly, when you think about Cayley tables in that way, you suddenly have this view that, in fact, every finite group is, in essence, isomorphic to a certain permutation. So far from being a kind of one particular narrow, minor sort of a group, the permutation groups, they suddenly become universal. Everything, meaning every finite group, is in fact, can be realized, can be represented as a group of a certain set of permutations. And that's something which we delve into and discover a lot about in the third year course group. And it kind of says on it's when you first meet that result, it kind of seems like a simplifying result. In that you say, okay, well maybe the world of groups isn't that complicated because everything is just a permutation group. So just study permutation groups and understand them. But actually, that's not really the sense of it. The sense of it really is to say that permutation groups, as maybe as simple or well-defined as they might seem, are actually just as complicated as the whole universe of groups. That's really the import of the sense. So it's not saying the universe of groups is simple because everything is a permutation group. It's saying the world of permutation groups is as complicated as the whole world of groups. So it turns out that groups, when you look at the whole collection of groups, that there's an extremely rich structure there, and still lots of things that aren't understood very well enough. Okay, so that kind of finishes that chapter. There's a few little things mentioned on after the exercises there. Just going further, but that's just kind of just a little taste of some future things. Certainly not examinable at all. But I've got some copies here of a previous exam paper from 2014. This is one of the ones available on Moodle. So I'd just like to hand this out to you now. Maybe get time to do one of the little question parts in it. But when I see you tomorrow afternoon, we'll do some more work with the questions to this. So there's at least 2 other past exam papers available up on Moodle from last year in 2013. Sorry. And we'll discuss some of these problems when I see you tomorrow. I'm trying to do a permutation on this now. I'll see you tomorrow, the next week. And there will appear on Moodle, put them up soon, some work solutions to the other examinations. You look like you
Yeah, only one left.
Okay, we've just got a couple of minutes left, so let's have a go of at that last one, question 1, part D. Since we've just left this topic of looking at permutations, so see if you can smoothly and efficiently discover the disjoint cycles that there are in this product of cycles, which are certainly not disjoint. A number of labels, namely 6, 6, 7, 7, 2, 2. There's a number of labels in common between these different cycles. These are not disjoint cycles. There are a sequence of permutations here, this first one, second one, third one, fourth one, fifth one, that are applied in sequence. This one first, then this one, then this one, then that one, lastly 2, 1. This is composition. This after this, after this, after this, after this. So this is the first one. And they operate on the elements 1 through 7, but there is some commonality in the elements that they operate on. You certainly can't freely interchange the order that these permutations are applied in. They won't commute in general. So let's see if you can discover what the disjoint cycles are within this. You can help to do it visually. I mean, you can just kind of do it all in your head, so to speak. But it also helps to trace out the action of the thing on the page. So you can just scatter the elements 1 through 7 anywhere on the page, and you start to look at what sigma does to each of the elements. Let's choose 7 as a starter. Why not? So where does 7 go? So there'll be some arrow emanating out of 7. The first one, what does that do to 7? Nothing. Leaves it unchanged. So 7 is the intermediate value that gets passed on to that one. That one again does nothing to 7. So 7 is unchanged, so 7 is the intermediate value that gets passed on. So remember, you're applying all of these, one after the other, to the original argument 7. Now, if that third one is doing something to 7, it sends 7 onto 6. So 6 is the intermediate value that then gets acted upon by that second last permutation there. But 6 is not mentioned there, so 6 is left unchanged. So again, 6 is the intermediate value that gets passed on. And the last permutation, transposition 2-1, again leaves 6 unchanged. So in total, when you feed 7 in at the beginning, it gets moved to 6 halfway along, and then that 6 stays where it is through the rest of it. So in total, 7 goes to 6 by under the action of sigma. We're drawing here the actions of sigma. So then you ask, well, okay, so now we discovered the start of this cycle is 7 goes to 6, so we should see how it continues. What does sigma do to 6? Well, where does it send 6? It sends 6 to 5. Isn't it? The first one sends 6 to 5. So 5 is the intermediate value that gets passed on, but then none of the other ones mention 5. So 5 is always left unchanged. So you then ask what happens to 5. 5 gets sent to 1 by the first permutation. So 1 is the intermediate value that gets passed on. 1 is sent to 1 by this one. 1 is sent to 1 by this one. But this one sends 1 to 7. So 7 becomes the intermediate value. And then the last permutation leaves 7 unchanged. So in total, when you feed 5 in at the beginning, it turns into a 7. So that's actually the closure of that 3 cycle. So there we discovered that within sigma there is this cycle of 3 elements. Even nicer, pick up a different color pen and start somewhere else. Just start somewhere that hasn't been mentioned yet. So 4 hasn't been mentioned yet. So there's some arrow coming out of 4. Where does it go? Well, in an intermediate stage, 4 gets sent to 2. And the 2 gets sent to 3, and the 3 remains unchanged. So in total, 4 gets sent to 3. Where does the 3 go? 3 goes to 7, 7 goes to 1, and 1 goes to 2. So in total, 3 goes to 2. Where does 2 go? 2 goes to 4, there, and thereafter 4 is left. 4 is left alone. So 2 in total goes to 4. So we've got the closure of that other 3 cycle. 2, 4, 3. So where does 1 go? Well, without looking, I know it has to just go to itself. Okay? Because 1, there is an arrow coming out of 1. And where does that arrow arrive? Remember, these are bijections. They're one-to-one functions. So the arrow can't arrive at any of the other elements because they already have arrows arriving. The only thing that doesn't have an arrow arriving at it is 1 itself. You can confirm that by looking at what each of them does to 1. So this first one sends 1 to 6. 6 is left unchanged. And 6 is sent to 2. 2 is left unchanged. And finally, 2 gets sent to 1. You feed 1 in at the beginning, and 1 pops out at the end. So sigma, as a product of disjoint cycles, looks like 7, 6, 5, after 3, 2, 4, 2. Or any equivalent representation. There are many different ways to represent just those 2, 3 cycles, but it just amounts to either changing the order in which you're composing them, which is fine because they're disjoint. These are disjoint cycles. And each one can be represented by a different string of numbers as long as they're in the same cyclic order. Okay? Remember, these are cycles. They don't have a start point and an end point. It's just a set of objects arranged in a cycle. Okay, so we'll do some more practice with some of these past exam questions. I'll start working through them methodically. And I'll see you tomorrow afternoon. And again next Wednesday then as well. And there's lots of other past, well, there's 2 other past exams there, so lots of other questions with which to practice. And there will be some more solutions, past exam solutions, put up on Moodle as well, for you to reference as well. Okay, so we'll leave it there for this morning, and I'll see you tomorrow.